Thank you.
So what we're going to be talking about here today is a new type of problem, very similar to what we've already been what we've been working on, called proving an identity. I know you're scared of the word prove, but it'll be okay. It is just like what we've been doing, except this time they've told you where you're stopping. Okay? Everybody feel good? All right. So we're going to start with a non-trigonometric situation, right? We can ask you to prove identities for things that are purely algebraic. We're going to start there before we layer the trig identities on top of it and kind of just talk about the process. So the same things that we've talked about in terms of algebra techniques we can use and identities that we can use, all that stays the same. And more or less it's going to be used the same way. So if I look at x squared minus 1 over x minus 1 minus x squared minus 1 over x plus 1, and that's supposed to equal 2, my job is to show how we start here and end there. Okay? That's how you answer a proof, it's the work in between is your answer. Because you have the start and you have the end. Your job is to supply the steps in between. Is everybody okay with that idea? So when you're like answering a question like this on a test or quiz, literally your work to go from start to end is what I'm going to be looking at. That's what I'm going to be grading. So if you don't show that well, I can't give you points for things. If you do too much in one step where it's difficult to follow what you did, I can't give you points for things. Because you have the answer at the end. It's not about the answer, it's about the journey along the way. Does that make sense? I know, it's very deep. All right. So the typical strategy that you want to do is you want to start on the more complicated side, because it's kind of like walking downhill. You could start on either side, but the less complicated side is like walking your way back uphill. It's usually harder than starting on the more complicated side and walking down. Is everybody okay there? So clearly the more complicated side is the side with all the fractions, because 2, you don't get any simpler than that. So if I have fractions, what are some of the things that you might think to do? So if I have 2 fractions, they're being added or subtracted from one another. You should think of 2 possible things that would be helpful here. You might be able to reduce the fraction so you don't have any fractions at all. Or you might need to make a common denominator so you can combine the fractions together. Which should we check first?
Reduce.
The reducing. Why? Because who wants fractions any longer than you have to? If I don't have to have them there, if I can reduce them out and like, poof, they're gone, that would be best. Everybody agree? Okay. So, to reduce fractions, what do I have to do when they have like polynomials in the fractions? Factor. I have to factor first. Excellent. Everybody remember this? You would have worked on this with Mr. Boyle last year pretty extensively. So, x squared minus 1, does that factor? Yes, how does it factor?
X minus 1.
X minus 1, x plus 1. It's a difference of 2 squares. Does everybody see that?
So I put the x squared minus 1?
Yes. Actually, we should do this first. Put it as a good example. Okay, so we factored the numerators, right? I started by rewriting the start of the problem. Can I factor x minus 1?
Yeah.
The denominator, x minus 1, can I
Oh,
factor
no,
that? No. Okay. How about x plus 1, the other denominator?
No.
Okay. Everybody feel good as to where we've gotten to here?
Yes.
Okay. Why were we factoring again? What were we trying to accomplish?
Reduce.
To reduce. Great. Perfect. That's exactly right. Do you see any reducing we can do in the first fraction?
X minus 1.
The x minus 1s can reduce. Perfect. And in the second fraction?
X plus 1.
X plus 1s can reduce. So what are we left with now?
X plus 1 minus x minus 1.
Do I need the parentheses here?
Yeah.
Okay. Is everybody good with what we've done so far? Okay, what do I do next?
Do you like multiply?
Well, what is the operation between the two sets of parentheses?
Subtraction.
Do I FOIL to do subtraction?
No.
No. So should I multiply?
No.
No.
Can you apply the subtraction sign as a negative to negative x to positive 1 and then add all together?
Yeah, so the only parenthesis that really needs to be here currently is the second one. The first one, it's fine to write it, but we don't need it because there's nothing going on in front of it, right? So what Kendall's saying, though, the second parenthesis definitely needs to be there because we need to distribute that negative sign through. So negative of x is negative x. Negative of negative 1, though, is positive 1. And then if we combine like terms, x and negative x, and 1 plus 1 is 2, and what were we supposed to end with?
2.
2, so are we finished?
Yeah.
Yes.
So you don't have to like use a identity.
Well, were there any trigs in this problem? There are no trigs in the problem, so there's no identity to use, because we didn't have any sines or cosines or tangents or anything in the problem. That was just a starting example, where we just like, I'm going to cut the amount of options we have to try in half to try to make the process a little bit easier to get your heads around, at least the algebra half of it. The next examples will have tricks in it, so now your identities will come back and talk about it. So at the end of our problem, when we finished, we put a little box, like a little shaded box, that's like our period at the end of our proof. And our proofs run horizontally, okay? Where we start at one side and we end with the other, right? Yes, Gianna?
So can we not like touch the other side at all?
Correct. We're not touching the other side at all. So notice that we started our proof there, and we end our proof there. So we work on only one side. We start on the left and end with the right, or we could start on the right and end with the left. Either is okay. But again, pick the more complicated of the two sides is usually the best route. And I say usually because if you see what to do the more complicated way and you see it first, then it's the easier way, right? Even if it's more complicated, like don't overthink it. Does everybody kind of see what we're doing here? Does this feel much different than what we've been doing? Not really, right? And in fact, it's kind of easier in a way because you know what the answer that you have to get to at the end is. So if you've made an algebra mistake, or you've made a mistake with your identity, you know, because you're like, I just can't get it to end with the correct thing, so you know to go back to look for something, right? It's like, you have the answer already on your piece of paper. It's like checking your work, right? If it doesn't check out, you know you've made a mistake. You go back and look at it again. Let's look at the next one. So here we've brought trigs back in. So we have tan x plus cotangent x equals cosecant x times secant x. So the first question I'm going to ask is, which side is the more complicated side?
The tangent.
The side with the addition, correct. Because on the side with the addition, you have two things, two different discrete terms, and on the right-hand side, you have one discrete term. You have two things multiplied together, like a 2x. You guys see that?
Mm-hmm.
So let's start on the left. All right, so if we look at this, there's no algebra thing to do here, right? Because I just have two things that are being added together and they're unlike terms. There's no fractions, there's no factoring that can happen, like it just, there's nothing to do algebraically. So we're gonna need to use an identity, right? Is it clear to you which identity to use?
Reciprocal for cotangent.
So maybe you rewrite tangent as 1 over cotangent, or cotangent as 1 over tangent. Maybe you write them both in terms of sine and cosine. Maybe you write them both in terms of secant or cosecant. It's not really super clear which one of those would be the best route, because they all seem like decent ideas at first glance, right? Does everybody kind of see? So sometimes it's worth taking a look at where you're trying to get to make a decision. So cosecant times secant, this is really the same as like 1 over sine x times 1 over cosine x, right? Which is like the same as just 1 over sine x times cosine x. So if I can get to here, I know I can go back to this, correct? So maybe I'm like, I would think, if I look to try to get there, maybe writing everything in terms of sine and cosine is the best route. Now, all those other suggestions we made are all plausible. They will all work. You'll get there. Maybe it's a little messier. Maybe it's the same amount of mess. But I think like on a problem like this, getting everything in terms of sines and cosines is maybe the best one. Not guaranteeing it, but it's probably going to be the least fraction-y, where you have like fractions inside of fractions and something gets real messy. This I think will be the neatest. Is everybody okay? So we're going to use Q1 and Q2 on this same step. Now again, are you required to write the names of the identities above the equal sign when you do this? No. Why am I doing it?
Show us.
Yeah, because these are notes. If you're going back and looking at this, like, what the heck did he do here? At least gives you a breadcrumb trail if you're going back and looking at this thing like, what happened? Everybody good? All right, what should I do next? Yeah, now it's going to be a common denominator time, right? If I look at these two fractions, sine x over cosine x and cosine x over sine x, what would the common denominator be? Good, sine x times cosine x would be the common denominator, right? So the first fraction will multiply by sine x over sine x, and the second fraction by cosine x over cosine x. Is everybody okay with what I've done here? I'm gonna try to change colors when I do something like make a common denominator or whatever, so it's clear what's, if you go back and look at it, it's a little bit more clear what happened. Is that cool? Okay, how do I multiply fractions? Because I have like sine x over cosine x times sine x over sine x.
Sine x squared and cosine x squared. And
Perfect, yeah.
Sine cosine x.
Perfect, yeah. Straight across, right? Everybody agree? Okay. And I'm going to write this next result as just one fraction with the common denominator. Everybody's okay with me doing that? Right, so we just made a common denominator, wrote it as a single fraction. See anything good happening here?
The top equals 1.
Yeah, sine squared plus cosine squared, that's one of the Pythagorean identities. Now, and that's basically exactly what we're looking to get because we know how to get from here to the finish line, right? Before we finish this out though, Gianna, how did you know that we wanted to look at the numerator for the thing to do?
What do you mean?
Did you notice that this
Because that's,
was the same thing that we were looking for
yeah.
over there, right? So we knew whatever we had to do, the denominator should be set. That's done. I don't want to mess with that because that's where I want to land later on. Is everybody okay? So to the finish line, I'll just rewrite this as 1 over sine x times 1 over cosine x. And then I use, I think that's R1 and R2. Is that right? I forget the numbering.
Yeah, I use that.
Yeah. Oh, got it. Come on, Mr. Kulik. And those are R4 and R5, I think. Going the wrong way. And again, that's where we want it to end at, right? So it's an example of sometimes it's an effective strategy to kind of work a little bit on both ends and then try to tie them back together again, right? If I can get a little way in. What's up?
Never
Ed?
mind.
You got it? Was it my bad penmanship?
No, I thought that because it was 1 over sin, I thought that it would be 1 over CSC, but I guess it's not.
Oh, okay, perfect. I love when you answer your own questions like that. We okay with this example? We'll go on to the next one then. If I'm moving too fast on any of these, or if you have questions, please speak up and we can spend more time, or I can elaborate or go into more detail or write out some more steps or talk a little bit more about the decision-making process that we use kind of like internally. So the next one we have 1 over secant x minus 1 plus 1 over secant x plus 1 equals 2 times cotangent x times cosecant x. Which side appears to be the more complicated of the two?
Left.
The left side, right? You have two things being added versus multiplied. Addition is more complicated than multiplication. plus we have fractions on the left-hand side, screams the more complicated of the two. So let's start there. And what does it look like we should do as our first step here?
Common denominator.
Yeah, common denominator seems like pretty obvious, right? What do I need to multiply the first fraction by to get a common denominator?
Secant plus 1.
Secant x plus 1? And the second fraction will multiply by?
Secant x minus 1.
Perfect. Excellent job. Oops. It's like a gnat flying around in here, just like buzzing my head. Or a fruit fly or something. It's really kind of obnoxious. You won't be able to see it, Chris, because it's like a fruit fly, unless you have like just unbelievable vision. No?
No.
I saw you looking like what's flying around in here. I know you're afraid of the water, but or oceans. I didn't think bugs were a problem. All right, should we keep going? What am I going to do here now? I've made a common denominator.
Multiply them?
Yeah, rewrite it as a single fraction, right? So multiply the stuff together. Will I bother multiplying the bottoms together?
Yeah.
I will this time. A lot of times I wouldn't bother. Why will I do it this time as opposed to many other times? What's special do you notice about these denominators that would make it a good idea to multiply them together?
It's going to be an identity.
Well, at least it's a difference of two squares, right? Which often is going to result in an identity. So maybe I'm not sure it's going to be an identity at first glance. I think that Gianna's been studying her sheet there while we've been talking, so I think she sees where we're going, which is great. But if I see like a difference of two squares, multiplication pattern, those are good. Like almost always I'm going to want to FOIL that out because it's going to end up giving me a Pythagorean at some point that I can use.
So does it matter if you put like the subtraction one rather than the addition on the bottom? Since it's still the difference of two squares, it doesn't matter if you put the plus one instead of plus one.
Oh, it 100% matters.
Oh, wait, no.
Well, right, that's the multiplication pattern. Right, if I FOIL this out, I'd get like a squared minus ab plus ab minus b squared. If I write plus b squared there, that's like a totally different thing that's not equal. Is that, it's okay?
Yeah.
Okay. So definitely matters, right? What to do next? We wrote it as a single fraction. What do you want to do now?
The identity is tangent x squared.
Okay.
Can't you reduce one of the secants on the bottom?
You can't reduce the fraction the way that you're asking to because of the addition and subtraction in the numerator
Oh,
and the addition and subtraction in the denominator. Right? You can reduce a whole thing, but you can't reduce part of an addition or subtraction problem.
okay.
Does that make sense? You can reduce part of a multiplication problem. Does everybody kind of see? And my example is usually like, if I have like 3 plus 1 over 2 plus 1, that should be like 4 over 3, right? If I reduce like Addie was suggesting, I would get 3 over 2. And if you tell me 3 over 2 is the same as 4 over 3, you're going to meet me after class. We're going to do some currency exchange. Where I'm going to give you 4/3 of a dollar and you give me $1.50 back. And I'll do that until I have all your money.
Yeah.
Yes,
Can I
Laura.
go to them?
Sure. Okay. All right, let's get this stuff out of here. This is all asides. All right, so Gianna says, let's do an identity on the bottom. What letter is the identity there, Gianna? It's P3, right?
Yeah.
Okay. And P3 says that secant squared is equal to tangent squared plus 1, right? So we can replace the secant squared with a tangent squared plus 1. So like this is turning into that.
Yeah, I thought it was just tangent squared.
Right. So like the plus 1 and minus 1 will cancel.
Okay.
Right, and leaving you a tangent squared. Let's do the same combining in the numerator though, right? Might as well, as long as we're doing one step, combine some like terms up top too. Does everybody feel okay with how we've gotten to here? Now it's going to be a little bit of a chore to sort this out. Okay? So my suggestion now is I'm going to write the 2 separately. And I'm going to write it like this. So no identity got used there. This is just me rewriting this complicated fraction as like a couple of different parts because I'm about ready to like do some identities here that's going to make like fractions on top of fractions, and it gets really messy if I'm not careful about how I want to do this. So before I do that, I tend to like to unstack them because it just makes it easier to follow what's going to be happening. Addie.
How can you cancel out the ones on the bottom of the tangent?
Because I combine the like terms of plus 1 with minus 1, which gives us 0.
But isn't it like what you said, like it's one multiplication?
I'm not reducing, I'm combining like terms. What is 1 minus 1?
0.
0, right? That's all I did. I just added 2 things that were next to each other. Or subtracted 2 things that were next to each other. I didn't reduce a fraction. Do you see how it's different? Because they're on the same level, right?
Also, why did you take out the 2?
So, keeping in mind where I'm going, I'm moving the 2 there because I know I'm done with that part, right? What I need to do now is I need to somehow turn this secant over tangent squared into cotangent times cosecant. So that's the part that I'm going to try to sort out now. Because the 2 part I'm good with. I have that part locked. Not touching that guy. So far so good?
Yeah.
All right. So probably what I want to do now is I want to rewrite this 1 over tangent squared as cotangent squared. Because if I look at where I'm going, I need to have a cotangent in there too. Is everybody good with the reasoning there? Again, I'm always, before I make my decision, looking at where I'm trying to get to see if I'm going to be getting closer or further away from my intended destination. And it's true, sometimes you have to take like 1 step back to take 2 steps forward. That happens on occasion. But I want to try to avoid having to do that if I don't have to. And that, what would I do there? I did R6, I think. Is that right? To go from 1 over tangent to 1 over cotangent, or cotangent? Yes?
Yeah.
Okay. I don't have the numbers, like I know all the identity, it's the numbers that kill me. All right. So now, if I look at where I'm trying to get to, I have a cotangent now, right? So I'm going to separate that. Cotangent squared is the same thing as just cotangent times cotangent, right? You see what I've done there? Where I've separated the cotangent squared into cotangent times cotangent. Because one of those cotangents I'm keeping no matter what. It's done, it's locked. So what I'm really left now is just trying to turn secant times cotangent into cosecant, right? Oh. You guys are so loud in the hallways. So right, like that's all I'm trying to do now. I want to turn secant times cotangent into cosecant. Once I've done that, then I know I'm finished because the rest of it I've got. Is everybody okay? How should I go about trying to do that?
A cotangent, CSC over secant.
Yes, perfect. So that's Q2. So we can reduce, and that's our finish line. What's up?
I'm lost. Why is this important?
Because it's lengthy.
Wait, why? How did you get the 2 in front of the cotangent? Because isn't it only in front of the secant?
Well, it's, so if I have 2 times x times y, that's the same thing as x times 2 times y, or y times 2 times x, or x times y times 2, right? If it's just multiplied together, I can move those, I can multiply in any order I want, right?
So you just factored the 2 into.
I didn't even factor, I just moved it inside the multiplication. You'd say commuted, maybe. Oh, and of course. Is that okay, Addie?
I want to stop. Yeah.
So, again, multiplication, the order doesn't matter, right? 2 times 3 times 5 is the same as 5 times 2 times 3 is 3 times 2 times 7. You know, like it doesn't matter.
Oh wait, so you just made it one
Like chungus?
thing, and you just multiplied them together?
It's been one thing, I've just been like peeling it apart, right? We were one thing all the way back to like this step, we were one thing, right? We've just been like
No, I
slowly peeling it apart, trying to get, you know, I had the 2, then this stuff has to turn into a cotangent times cosecant, right? I turned 1 over tangent squared into cotangent. There's a cotangent piece, so I'll peel that off. Now I have just secant times cotangent that has to become the cosecant piece. And then I identity those so I could do some reducing, and secant, cosecant falls out, and then I'm all done. Let's do another, eh? I think I have one more example for you guys. And then it's your turn. Oh, I have 2 more examples.
Cosine, the second one.
So it's cosine t over 1 minus sine t equals 1 plus sine t over cosine t. Again, t you could just replace with x's if it's more convenient for you. Krista? Sure.
So how do you pick which one is harder?
Right, yeah, that's a great question. What do you think?
Is it that way? I don't know.
They're probably gonna be about the same.
Like the one with the multiple letters, multiple things in the bottom.
Is the harder one?
Yeah.
Okay. I think it's gonna be 6 and 1/2 dozen the other. I don't think there's a wrong choice here. I think they're both gonna be basically the same procedure, just upside down,
Okay.
you know? But sure, we'll start with this side. Do I have any algebra thing to do here? No, right? Nothing obvious, right? Do I have an identity thing to use here?
Wait, can you make it cotangent, like 1 minus cotangent?
No. If it was the other way around, if we had started with the other side, you can break a numerator apart into pieces with a common denominator, but you can't break a denominator apart into 2 fractions. That's actually a really difficult task. So this doesn't look like anything obvious to do, right?
Yeah.
So here's an example of where looking at where you're trying to get to can be really, really helpful. So if I look to where I'm trying to get to, I need to have a cosine in the denominator, right? Guess what I'm going to do? Let's just do that and force a cosine into the denominator. Everybody okay? Nothing wrong with me doing that. So I have cosine squared now over 1 minus sine t times cosine t. And that part is locked, right? I don't want to touch that cosine t in the denominator because that needs to be my final answer anyway. So that is not getting touched. I'm going to avoid doing anything to that. So if I look at my end, somehow this cosine squared t over 1 minus sine t has to reduce down to 1 plus sine t on top.
Oh, cosine squared can equal 1 minus sine squared.
Perfect, yes, exactly right.
And then can you cancel out one of the 1 minus sine squared in the bottom?
Well, you gotta do something first to the top because you can't reduce it the way it's currently written. But I want to pause here for a second, Gianna, because I'm not sure everybody has seen or understands how you went and did that.
Oh, it was.
Nope,
Oh, yeah.
I'll do it. But I just want to pause because I'm sure that there's somebody in there going, wait, that's not on my identity sheet. I just want to point out what happened here. So on your identity sheet, we know that sine squared plus cosine squared is equal to 1, right? If we rearrange that identity by subtracting sine squared from both sides, you're left with cosine squared is equal to 1 minus sine squared. And that's what Gianna used in the numerator there, was that rearranged version of P1. I would suggest to you on your identity sheet to rewrite or to write those additional rearranged versions of P1s on there, that cosine squared is equal to 1 minus sine squared, and that sine squared is equal to 1 minus cosine squared. Those are really handy to have, which you can use just the same way as you use P1. All right. So Gianna wants to reduce 1 minus sine squared t with 1 minus sine t. And I told her we can't do it as it's currently written. We have to do something in the numerator first. Do we see what we need to do to the numerator first?
Split it up. So like 1 minus sine squared and 1 plus sine squared.
Yes, so we do need to factor. And that numerator is a difference of 2 squares. So we 100% can do exactly what Gianna suggested. That's great. And now that it's in factored form, we can reduce. And what has happened? We landed where we needed to. That was where we were trying to get to. We finished. Yay. Right? Yay. One more example. And then time for you guys to try some on your own afterwards.
Is our homework a worksheet or is that one note?
It's going to be the homework, some of the more of the homework rounds out of the book. All right. Okay.
Just how
Which side do you want to start with? I think that's fine. I think, again, this is going to be a situation where it's kind of like 6 of one, half dozen of the other.
Is your day? I'm gonna join her. No, she's there. There is. She's also her. She'll probably also keep. I mean, you do. I'm sorry, it's disgusting. I'm disgusted.
Okay, what do we want to do here?
Can we do P2 on top?
What's P2 on top going to give us?
Cotangent squared is CSC squared minus 1.
Okay. Seems okay.
Break up the CSC squared minus 1.
So factor, yeah. If we're going to go this route, that seems like the obvious choice.
She said E, so I know he's gonna type.
Can you cancel out the CSC plus 1?
Are these the same?
Yeah. Yes.
Yes, they are. Why are they the same?
Because the one is positive, so I can just move to that.
Addition is commutative, right? If these were this was 1 minus CSC. Those are not the same, right? They differ by -1, so you have to factor -1 out. But here you're safe to do as you direct, or as you instructed.
You would have never expected that. You would have never seen it. Maybe something.
Now what do you want to do here?
There's something following. There's something
I see is like making like one over sign. Can we do anything else?
You can make the CSC 1 over sine. I would not. I think that's going to be the longer way to get there. I'm going to do a sneaky thing here as my suggestion.
Wait, can we divide it by side so we can have cotangent?
Well, what I notice is that I need to have a tangent, or a minus tangent, and I have a -1. Everybody see that? What if I take this then and multiply it by tangent over tangent? Is it okay to multiply by tangent over tangent?
Yeah.
Because it's just multiplying by 1. Everybody agree? So I'm actually maybe better off thinking about this as, let's think about it this way. Instead of writing as tangent over tangent, I'm going to write it as tangent over 1 times 1 over tangent. Same thing still, right? But I want to distribute one of them and leave the other. Why would I do that? So I'm going to have the tangent here, and by leaving 1 over tangent outside, what do I get? The cotangent that I need out front. Ooh, this is starting to look pretty good, Mr. Kulik. Yeah. All right, so we did R6 to make that guy, oops, at some point I lost my U's. I did kind of a lot there. Do you guys see what I did? Let's go back to what we're trying to get to. I have a cotangent out front. That part's locked. I have a tangent on the inside. That part's locked. So somehow now this secant U has to come from this, right?
Yeah.
Perfect, yes. Yeah.
Random shit.
And then we're at where we need to be, right?
You should just say, what do you say, just how are you? I'm not the say, you should say, oh, you
Now that was rough, right? What was the trickiest piece?
The like 1/2 tangent and that.
Yeah, when I multiplied and divided by tangent in the same step.
Wait, will it be pulling down the text? I feel like I would not remember to do that.
Well, let's look at what happens if maybe we chose to go the other direction.
Like so it would be
Yeah.
easier.
Maybe. Right? There's no reason if I compared the two sides, other than the left-hand side's a fraction, there's nothing inherently about the left-hand side that screams that one is much more complicated than the right-hand side. The right-hand side's fairly complicated on its own right.
Bless you.
That's very good.
just for now. Can we actually try to do that? Probably. No, these are the stage. Okay. She's talking, she can actually see.
So what do you think we would do first if we decide to work on the right-hand side?
Make the tangent CJ over CSC, because we can have CSC in the bottom.
Well, I mean,
Yeah.
possibly, yeah. What I would say is that certainly that cotangent front is staying there, right? I don't want to mess around with that because I've already got a cotangent. I need to have a cotangent squared in the numerator, so that right there, I'm not too upset that there's already a cotangent there. So I'm eventually going to need a fraction out of this though, right? So I got to get a 1 plus CSC down there. Let's maybe rewrite that in terms of sines and cosines and kind of see how that goes. To do some combining of like terms and make a fraction. What do you guys say to that?
Your HUA.
Is everybody okay there? I just used what? Like that's R2 and then Q1, right?
He's not just like a
Yeah, just do it.
You could be like, go see my old drafts. And have that old drafts, this is my fall.
So far, so good?
With kids at home,
Okay.
actually.
I think at this next step, what do I want to do here?
Can you
Yeah, but
multiply
I found this draft that emoji skull.
1 minus sine,
Father,
and then do
well, you could just post something like 1, 2,
plus
like, just do like
sine
emojis, picture
on
and
both to both sides, and multiply by 1 plus sine.
Yeah. We can do that. That seems like a reasonably good idea.
She's so I love sports. She's obsessed with that. And all my sports teams too. So she's a sophomore. She's a sophomore. She's a sophomore in June. I remember my sister knows her.
Oh, we just watched messages.
See.
Video.
Anthony's friends.
Okay, you can make the top cosine square
Mm-hmm.
and then like split that up and cancel out the cosine at the bottom, right?
Sounds good.
If you just make the sign, like if you just do, it's like identity and just make it 1 over CSC, it's just like the one goes away, right? Because it's right on the bottom.
So this is, you're right there. We're almost there. So here is what you need to do.
Oh, or is it because the sign is written on the bottom, it just equals CSC?
No. This is the trick. Why am I doing that?
Yeah.
If I multiply that into the numerator, what am I going to get?
1 over sine squared. Cosine over sine.
Which is the other cotangent I need in the numerator, right, with this guy? If I multiply it to 1, what am I going to get? 1 over sine, which is cosecant. And if I multiply it to the sine, what do I get? I get sine over sine, right? Which is 1. Is that going to give me everything I need now? Yeah. So there was, again, we did not find a better route through here this time either. Yuck. Let's look at what I wrote for the key on this, see if, given the infinite time, if I came up with anything better for this problem. Oh, look at how nice that worked out. Oh, no, this was meeting the middle.
Wait, you did both sides?
Well, I met in the middle, was the idea. So I can take this work, and then from here, now just go backwards to there. is the idea. It's not really, like it looks like I worked both sides, but I just I did it so I could figure out like how to marry the two together, then I can just go from one side straight to the other side because I just walk in reverse.
But like you solved like the one side like to like an extent and then tried to do the other side to that?
So like what I did, what this would have looked like when I put it all together. Would have been and then I do like this. Which is equal to this. Oops. And I'm going to go here, which is equal to CSC over, well, let's just say times secant U over secant U minus tangent U over tangent U, which is here. And then I rewrite this as like, you know, cosecant over secant times 1 over secant. Oops. Times secant minus tangent times 1 over tangent, which is going to be cotangent times secant minus tangent times cotangent, which I factor the cotangent out, and now I'm back to the right-hand side. You know, so I just like didn't write it out again because I had the two. I just have to walk the one path in reverse instead of forward and marry them together to make it like a real proof.
Will there be ones like that on the test?
Here's what I'll tell you about the test. On these problems, there's gonna be like some set of them, and you only have to do like, you know, a certain number out of the set, and you have the choice to pick. So if you run into one and you're just like, I don't know I don't think I can figure this out in time setting, I have to do this. You skip it, go to one that's like, oh, I know what to do for this, and maybe only there's one that's like, gotta kind of stumble my way through this and fingers crossed. You know, there's 3 of them left. I have my choice of which one to stumble through. Like one of them, I hopefully, fingers crossed, can I get to work? You know what I mean?
Yeah.
So you have freedom there to avoid one if you're like, this is just not working out for me. Does that seem fair?
Yeah.
Yeah. Which again, these kinds of problems can be like, when you see it, right? After you've done enough practice, like I see exactly where I'm going,
Yeah.
and they're gonna come quick. And there's others that like, you stumble around and sometimes you get to the end and sometimes you're just like, I don't know what to do here, and you just feel like you're running in a circle. Those are the ones that you quit and like, I'm gonna try something else, I'll come back and look at this maybe later if I have a chance, but like, I think this is done as much as I'm gonna be able to do in a time setting to figure out.
Homework, Mr. Bullock?
Yeah, so what you guys should work on for next time is like,
What were the questions from last class?
they were 7 through 14. And this time we're gonna do 47 through 54, so those 8.
It was 1 through 7.
No, 7 through 14 was the first
Okay.
book set. We have not done any 1 through 7.
Okay, so just 7 through 14 and then that.
And then 47 through 54. And I'll get those up onto the assignment center here.
That wasn't due last week, though, right?
Correct. Yeah, that was part of this Sunday's problem set.
Yeah.
Sure.
Need it done. Yeah, and sure. Not a lot of show to
Yeah.
So, what's your decision?
You guys this bounce.
Dude, I haven't even written down maybe seven. I haven't done worksheets.
Everybody feel good about what's due when, what to do? Hopefully this doesn't feel like too much all dumped on at once, right? Been trying to build in time to do stuff in class. So yeah. Okey-doke. I'm gonna stop here. The last 15 minutes or so.